Okay, welcome back, guys. Hopefully, we will be able to do this without any more glitchy bits. So we've got two more on this slide, and then we got a couple other things we want to talk about. So I used 62.345 milliliters of a 0.1005 molar standardized NaOH solution to titrate a 75 milliliter sample of HNO3. How much HNO3 was added to the one liter volumetric flask to make this solution? So I'm looking to see what was the concentration to make this, right? So what is the concentration of the solution? Therefore, how much did I add to make this work? So standard process, I need to balance my equation. NaOH plus HNO3. I know it's 1H, 1OH, so H2O plus NaNO3. So it's a 1-to-1 relationship. I know that I have 62.345 milliliters of NaOH, and I know that is a 0.1005 molar solution. I mean, it's a 75 milliliter sample of HNO3. Now, I'm going to bring this down here. We're going to do the math down here. So 62.345 milliliters of NaOH, 1,000 milliliters per liter. Cancel that unit out. I know that I have 0.1005 moles of NaOH per liter. Cancels the liters out. I know there's 1 mole of NaOH to 1 mole of HNO3. That gets rid of the moles of NaOH. Now I need to have that volume in there, so I divide by the 75 milliliters that sample is, and then I convert the milliliters to liters. And if I do all of that happy math, 62.345 divided by 1,000 times 0.1005 divided by 75 times 1,000, and I end up with 0.08354 mole. And I've left this as 4 sig figs, looking at the numbers that I have. I have 5 there, but all my other numbers are 4 sig figs, so I'm leaving as 4 sig figs. So that is the correct number of sig figs on this, and I would report that. Okay. Now, since that's in 1 liter, that means that I needed this 0.0835 moles. And since it didn't specify it wanted to know how many grams, I'm going to leave it as that. If I wanted to know how many moles, then I could multiply that by the molecular weight to find how much it was. Next question says, I'm working with a sample of NaOH that is not pure, and therefore the mass of sample added to make my standard is too low. That standard is only 0.99639 molar, and I wanted to make it to be exactly 1 molar. It was the actual mass of NaOH, so it was added to 1 liter to make this standard. Well, okay. So I know that if I'm looking at this and it says that it's 0.99639 molar, right? Then that means that I've added 0.99639 moles, right? Comparative to the 1 moles that I wanted. So this is how many moles were added, correct? So if that's how many moles were added, 0.99639 moles, and the molecular weight of NaOH is 22.990 plus 15.999 plus 1.008, which is 39.997. Then I can multiply those two together. And 39.85 and 1, 2, 3, 4, 5, 3 grams of NaOH is the mass of NaOH that was actually added. Now, I probably added more to try and make this work, right? Probably tried to add 39.997 grams, but this is how much NaOH was actually in it, okay, to make this actually happen, okay? Now, if I wanted to talk about percent error and things like that, I need to make sure that that was the actual mass that I actually added. But this is how much NaOH was actually added to make this solution. Okay, questions, comments, problems on that? Okay, so that's all we were looking for. It's just that simple of a calculation. I wasn't looking for anything more complicated than that. I know it looked a lot worse than that. That's all I wanted. All right. So moving on. A couple other things we want to talk about when we talk about titrations. It's a little harder to see this when we talk about this in terms of the virtual labs that you guys are doing, because the virtual labs that you guys are doing don't really work with the indicators that we work with in the physical laboratory. So when we talk about labs in the physical laboratory and we're not working with, standard pH meters, we typically do these with a visual indicator. And then visual indicator is something that is itself weak acid or weak base that changes color when it goes through its change from an acid to a base. So when it goes from its acidic form to its basic form, it's one color in the acidic form, one color in the basic form. And so as it does that, we get a color change. Okay. So as we start to titrate it, we will see that color change. The presence of that color change is what we're actually looking for. It's our visual indication that the titration that we were looking at is done, and this other titration has begun. And so what has to happen, what is absolutely necessary, is that that endpoint detection has to happen past the equivalence point. Otherwise, it doesn't work. It has to happen past the equivalence point of our titration. Otherwise, we're not detecting the equivalence point correctly. Okay, so it has to happen past there. And therefore, we end up with this thing called a titration error, because we go through the equivalence point where our base exactly equals our acid. And then we add more of our titrant, whichever it is, and it's usually the base that we titrate with. We add more base, and then we start to titrate the indicator, and we detect the endpoint. And once we detect the endpoint, we stop. And so there's some gap between this equivalence point and this endpoint. There is some gap there. And we can, account for that if we can figure out how big it is and, get some consistency in how we do it and all the rest of it. There are ways that we can account for it, but it's not always the best way to do it. And it depends on which indicator we choose, how close those two things are. So we have to talk about where those happen and how they happen, and look at the choices that we're making to see how close they are. So we have to look at these indicators. Every indicator that we deal with is a color change. So we can talk about crystal violet. It goes from green to blue. And it does so over a finite pH range. So we're looking at it going from like 1 to 2. So right here in the 1.5 kind of range. We hit this transition between green and blue, and that's the color change that we're looking for. So when it starts to go from green to blue, we start to see that transition. That's what we're looking for. We've got methyl orange, and it goes from red to orange. And of course, that color change, that's what we're looking for, is when it goes in between those two. Bromocresol green goes from yellow to blue. And so this green that we hit in the middle is what we're really looking for. Methyl red goes from red to yellow. And so we're looking for this orange that happens in the middle. Bromothional blue goes from yellow to blue. And so there's sort of this greenish color in the middle that we're looking for. Phenolphthalein goes from clear to this bright, obnoxious pink. And so what we're looking for is the palest pink that you can possibly see. And so you want it to be barely detectable as pink is the color that we're looking for. And of course, there's a couple of factors in that. One is how detectable is the color? So how little of it can we detect within our own eye change? And color is a subtle thing. Not all eyes are very, good at detecting that color change. All right. The other thing is that this may happen very far away from the endpoint that you're trying to detect. So if your endpoint actually happens like right here, and you have to pick an indicator for that, the best choice you've got is this one. But look at the difference between those 2 points. I mean, we're talking about going from here to here. That's a big pH difference. Remember that, well, okay, just in case you don't know, that pH value, that's a logarithmic scale. So it's a big difference. And so, we're talking about huge differences in concentration between those 2 places. But that may be all we've got. And so there are other alternatives that we can use other than just visual indicators to try and help us to do this. Okay. But if that's all we've got, that's all we've got. Right? And sometimes that is all we have, especially in a lab like what we're working with here, because visual indicators are cheap. Other means, not so cheap. So we may not have anything else to work with. So we have to pick an indicator that's within the right range that will change past the equivalence point we're trying to detect. So if the change that we're looking at happens like right in this range right here, we've got to pick something that changes in that range, but it needs to change past this. So we can't pick this one. We can't pick the one that's below it. We've got to pick the one that's above it because it has to happen past. Okay, so we have to make the best choice we can make. Okay, and it becomes a very, how do we do this? How do we fix this? How do we make the choice that's the best? Okay, we want to minimize that titration error. We've got to make sure that we have that available. Okay, so again, titration error is defined as the difference between the end point, the equivalence point, and the end point. So where we have added equal moles of acid and base, that's our equivalence point. And the end point, where we detect that color change. Okay. You will get asked. So just like we can talk about looking at acid-base titrations, we can look at the change in pH and the acid-base quantities that we have. We can also do something called gravimetric analysis. So I know that we can form solids from some of these reactions. And so what we can do is set up a reaction where we form a solid. And so we can drive this reaction so that we make a solid. And we can drive that reaction forward until we stop making the solid. And we can look at how much solid did I form to tell me what the concentration of the ion that made the solid was in the starting solution. Because if I form as much solid as I possibly can, that will tell me how much of that ion was in the starting material, right? If I know how much of this I make, it will tell me how much of the chlorine was present in the solution I started. Because I know I've added some of this, I know what this concentration was, then I can figure out how much of this there was available to me. Okay, so that's something that we can talk about. Now, let's take a look at what that math would look like if we wanted to do that. Bear with me just a moment, I'm sorry. Having some problems with my blood sugars today. Take care of that. So we're looking at this reaction between silver nitrate and sodium chloride, both of which are aqueous. When we mix them together, sodium nitrate is aqueous, but silver chloride is not. It makes a solid. And so we can drive this reaction. We have the silver chloride in the beaker, and then we have our our sodium chloride in the beaker and our silver nitrate in the burette. We can add the stuff from the burette, the silver nitrate, until we stop making solid. Okay. And actually, we can just make sure that we've added enough, and then we can dry off the solid, filter it, and measure how much we make. Okay. And based on how much of that solid we made, we can then figure out how much of the Cl was present. So what they say is that we have a 25 milliliter of an unknown silver nitrate solution is react with 15.631 milliliters of a 0.250 molar NaCl. Okay. So with this, in this case, we have more information about this. So we know 15.631 milliliters. And I know that this is 0.250 molar. And I know that I have a 25.000 milliliter sample of this. So I'm going to start with the one I had the most information about. I've got that 15.631 milliliters. Convert that to liters. Multiply by the molarity, 0.250 moles of NaCl per liter. It cancels the liters. I now have moles of NaCl. I know that 1 mole of NaCl reacts with 1 mole of AgNO3. No, sorry. I actually want to look at how much product it, because I need to relate it to how much, well, no, because I'm now measuring the bottom. Actually doing that at the moment. Got 1 mole of AgNO3. And so based on that, I get rid of the moles of the NaCl. I know that that AgNO3 sample was 25 milliliters. And then it's 1,000 milliliters in that liter. And so we can calculate this one exactly the same way as what we've done before. Okay, so 15.631 divided by 1,000 times 0.250 divide 25 and multiply by 1,000. And that gives me 0.1561. Check that math again. Just something about it looks weird to me, so I just want to check the math. I know. Okay. Yep. And so that's the concentration of the AgNO3 that I have. Okay. So we can do this based on the amount of the AgNO3 that we added. So that is a possibility. But we can also do it if we take this out and measure the mass that's left. So that's a true gravimetric analysis. Okay. Now, if we were to do the gravimetric analysis, we'd only know the concentration of the Ag+ ion, not the entire species. We're only able to look at the counter ion that we're, making the precipitate with. Okay. And we have to make sure that they're driven to completion, because if they're not, then we don't have any way to do this. So we've got to work with things that have very low solubility. Okay. Standardized solution of NaCl is 0.0526 molar. Titrating a solution containing lead-2 nitrate of unknown concentration. I use 56.245 milliliters of the NaCl to titrate a sample of 50 milliliters of lead-2 nitrate. What's the concentration of lead-2 nitrate? Gee, this looks familiar. So let's see what we got. So NaCl, a lead-2 nitrate. Pb2 plus, actually, I'm going to make this, sorry, I'm going to move it so I can. Pb2 plus NO3 minus. So it's going to be PbNO3 2. And that's going to give me. So I need to have PbCl2. I'm going to trade. So I need 2 of those plus NaNO3. And that means I'm going to need 2 of those. So 2 NAs, 1 Pb, 1 Pb, 2 NO3s, 2 Cls, 2 Cls, 2 NO3s. So everything is balanced in this equation. Okay. I know that my NaCl solution is 0.0526 molar. I don't know the concentration of this one, so I don't want that. I know that 56.245 milliliters of NaCl, 50 milliliters there. So we start with what we know the most about, and that's that Pb solution. So I have, oh, actually, it's not the Pb solution, it's this one right here. 56.245 milliliters of the NaCl, 1,000 milliliters in a liter. I have 0.0526 moles of NaCl per liter. Liters cancel. I have 1 mole of NaCl, or actually 2, because that's the number out in front is 2, or 1 mole of PbNO3. 2, and then that gets me 2 moles of PbNO3 2. Sample is 50 milliliters, and then of course tack this on because I can't fit it up there. There's 1,000 milliliters in a liter. Milliliters cancel there and cancel there, and that will leave you with an answer of 56.245 divided 56.245 divided by 1,000 times 0.0526 divided by 2 divided by 50 times 1,000. It's 0.02958. It should only be 3 sig figs, and then it's based on this number right here, 1, 2, 3 sig figs there. And I get the answer again. Okay. So that is my concentration for the lead-2 nitrate. Questions, comments, problems on that? Next question asks me, a solution of 0.0526 molar sodium chloride is being used to prepare a solution of 0.00053 molar sodium chloride. We need to use the 0.00053 molar solution to do the reaction and require at least 75 milliliters of that solution. How much of the 0.0526 molar solution do I need to dilute to 75 milliliters to make the desired solution concentration? Well, okay, remember once upon a time, we talked about M1, B1 equals M2, B2. Or the M's are molarities and the B's are volumes, right? So I know that my M1 is this number right here. My M2 is that number right there. And this is my V2. And I'm really trying to solve for V1. So I'm going to rearrange this. I'm going to solve for V1. So V1 is equal to M2 V2 over M1, right? So I can plug in the numbers that I have. I know that my M2 is the 0.000534 molar. I know the V2 is 75.00 milliliters. And my V1 is 0.0526 mole. Okay, now I'm going to do the math and see what I get if I do this. 0.00534 times 75 divided by 0.0526. And I end up with an answer that says 7.614 ml. Let me check that math, just make sure. 0.000534, and I think I made a mistake, times 75 divided by 0.0526. And I did. Okay. I left out a 0 right here, so that means that my number was off. And so I get 0.7614. Now I ask you, I know you haven't physically been in our lab, but do you know of any piece of equipment in the general chemistry laboratories that can measure that? My answer to you is no. We don't really have a way to be able to measure that volume in the labs that we have. It's very difficult to do so. And so it really can't be done. Since it can't be done, what could you do to solve that problem? How could you change this? What are options that you have available? And of course, you can think about this, talk about this, do whatever you want. But there are a couple of ways that you can deal with this. So you could do an intermediate dilution. So you could dilute that solution to something else and then dilute it again to get to the point where it's this concentration. So you could dilute it by, factor of 1 and then a factor of 2 or whatever. It's a process called serial dilutions, so that we can then get to the concentration that we need. So you might want to take your solution and dilute it to, say 0.00534, and then again to 0.000534, because then you can do 2 dilutions and make that work. Obviously, we don't want to have to do it, 8 billion times. So trying to do it in 2 steps would be a reasonable way to do this. Factors of 10 are usually good ways to deal with these problems. So doing that is reasonable. And going from 0.0526 to 0.00534 is probably a reasonable way to do it. Okay, those are different, but it is possible to make that change. So that's one way you can do it. There are other ways that it can be done, but that is a way that will typically work. Okay, so we need to do serial illusion. I'm going to say can't measure. So even though that's the volume that I should be measuring, I can't measure. Okay. Now, examples of barometric titrations: sodium chloride, primary standard, used to standardize the silver nitrate solution of unknown molarity via the following equation. 0.125 grams of NaCl requires 21.3 milliliters of AgNO3 to fully titrate. What is the concentration of the AgNO3 solution? The standard silver nitrate solution is now used to titrate a sample of potassium thiocyanate of unknown molarity, being the following equation. 20 milliliters of KSCN is added to an Erlenmeyer flask and is titrated with 31.5 milliliters of the standardized AgNO3 solution. What's the concentration of KSCN? I'm going to let you think about those two things. See what you can come up with as answers to those questions. I'm going to run off and do some thinking about it myself, and I'll come back and walk you through it, okay? All right, guys, we'll see you in a few minutes. All right, guys. So let's take a look at what we've been given here. Sodium chloride, NaCl, molecular weight 58.44 grams per mole, and it should say mole. Primary standard is used to standardize the silver nitrate solution of unknown molarity via the following equation. NaCl aqueous plus AgNO3 aqueous goes to NaNO3 aqueous plus AgCl solid. 0.125 gram sample of NaCl requires 21.3 milliliters of AgNO3 to fully titrate. What is the concentration of the AgNO3 solution? So what I did was I came down here and I said, okay, I have 0.125 grams of this NaCl. And I know the molecular weight is 58.44. So when in doubt, convert to moles. So I took that 0.125 and I divided it by 58.44. And that got me moles of NaCl. I know that 1 mole of NaCl per this balanced equation right here reacts with 1 mole of AgNO3. So that gets me to moles of AgNO3 right here. And if I divide by the volume of that solution, there's 21.3 milliliters of AgNO3 that are used in this reaction. And I can convert that from milliliters to liters, and that gets me 0.100 molar AgNO3. I got an answer. And I report that, 0.100 molar AgNO3. Now I come to this next thing, and it says this standardized silver nitrate solution is now used to titrate a sample of potassium thiocyanate of unknown molarity via the following equation. AgNO3 aqueous plus KSCN aqueous goes to AgSCN solid plus KNO3 aqueous. Okay. All right. I don't really know this reaction, but okay. 0.1 molar AgNO3 aqueous, 31.5 milliliter sample, because it says that down here. 20 milliliters of KSCN is added to an Erlenmeyer flask and is titrated with 31.5 milliliters of the standardized AgNO3. It's the concentration of the KSCN. So 20 milliliters of the KSCN, 31.5 milliliters of this 0.1 molar AgNO3. That looks familiar, so I can work with that. So 31.5 milliliters, I divide that by 1,000 to get my liters, multiply by the molarity, the 0.100 moles of AgNO3 per liter. So that gets me to moles of AgNO3. I know that 1 mole of AgNO3 reacts with 1 mole of KSCN because that's what this balanced equation says. Right up here, it says that they 1-to-1 react. So then I've got moles of KSCN. Well, I wanted that. So now I gotta divide by the volume. So I divide by the 31.5 milliliters that they told me. Wait, hold on, wrong volume. Oops. This does not go here. I have to divide by this volume, 20 mil. 20.00 milliliters. Of course, it's going to change its answer. Apologize. So 31.5. So I divide by the 20 milliliters that the solution is, and then convert that to liters and multiply by 1,000, and that should give me my answer. So I take my 31.5 milliliters, I divide it by 1,000, and multiply that times the molarity of that solution, which was 0.100. I then divide that by the 20 milliliters for this sample, and then I multiply that by that. Sorry, glitching everywhere. I don't understand, but I do that, and that tells me that this solution is 0.15, and it should be 8. Okay. I wrote it in the wrong place, but whatever. That's the one that goes with that particular KSCN solution. Okay. So volume that goes with our AgNO3 multiplied by the molarity for the AgNO3, 1-to-1 ratio between the AgNO3 and the KSCN, and then divide by the volume, the KSCN. Give us our answer. Okay. Questions, comments, problems on that? Hopefully not. Hopefully you're starting to see the process that we go through each and every time. Get to moles, either grams to moles, or we take milliliters times molarity to get to moles. From moles to moles of A to moles of B, whatever relationship that is. We use the stoichiometric coefficients in the balanced equation to figure that out. Then from moles of B to molarity by dividing by the volume, or mass by multiplying by the molecular weight. Okay? So those are our scenarios so far. Questions? I hope not. Now that takes us to the end of our concentrations lecture. So, like I said, next time we're going to come back with some very different stuff. No mathematics involved whatsoever. So, I will see you again soon. All right, guys. Thanks.